Example number 3, same process. As you can see though, this is a little bit larger two-variable function, so it's probably going to be more involved. All right, let's go ahead and get going. So let's first look at the first partial with respect to x. This is going to be, when we look at this is going to be 0, 0, 0. These are all considered to be constants because we're only looking at the first partial with respect to x. So we're going to derive this now, which will be what? 4x, and then minus 6, and this will be 0. Okay. The next one will be the first partial with respect to y. So what is that? Derivative of this would be 6y squared. This would be minus 6y, and this would be minus 12, and everything else would just be 0. Okay, so we create our system of linear, well, it's actually not a system of linear equations, it's a system of a linear equation and of a quadratic equation. Definitely making this a bit more challenging. Okay, with that being said though, if you notice, again, each of these equations is in terms of a single variable. So that's nice. So when we solve this one, we get what for x? We get x equals 3/2. And this one's just going to be a little more complicated to solve because it's quadratic. So I'll just rewrite it down here, and then we'll work this out. So let's go ahead and remember, if possible, you always try to factor out a GCF, greatest common factor. So at this point, I would divide both sides by 6. When I divide both sides by 6, this is gone. And let's see if this is factorable. I think it is. So we get that factorization. So therefore, y is what? -1 and 2. So what this means is, based upon x equaling 3/2, we now have 2 critical points. So let's write this down. We now have what? Therefore, critical points where? At 3/2, -1, and also at 3/2, but at 2. So those are our 2 critical points. All right? Okay, let's keep going. Let's go back over here and come up with our second partials for all these. So with respect to x, it's going to be 4. With respect to y, it's going to be what? 12y minus 6. And then our first with respect to x, second with respect to y is going to be 0. Okay, so now in this case, because we have 2 critical points, we have to run the second partials test twice. All right, you're going to run the second partials test for every critical point you have. So let's start by looking at it with respect to this point. So that would look like this. Now, hopefully some of you are seeing that this one and this one could have simply been written as a 4, and this one could have simply been written as a 0. Okay? Anyway, I'm just trying to show you the notation based off what the second partial test is all about and the discriminant. Okay? So, anywho, this is going to generate what I just said, a 4. Now, what's this going to generate? Well, what you need to do now is look at the second partial with respect to y. Notice there is a variable still involved here. And notice the variable is just a y. So because you only have a y here, you will only use the y coordinate in this critical point. So you're going to replace this y with this -1. So that'd be 12 times -1, -12, minus 6, which is -18. Minus whatever this is, which is 0, and then squared. All right. The bottom line is that this discriminant is going to be equal to what? Well, whatever this product is, which I believe is -72. Now, is -72 greater than or less than 0? It's less than 0. So because it's less than 0, you're looking at option number 3, which means we're going to get a saddle point. So, therefore, saddle point at f of 3/2 -1 equaling what? Well, you got to be able to plug in this x coordinate 3/2 and this y coordinate -1 into what? Into the original function to see what your z value would be that would, get spit out here. And in this case, it's 7/2. All right? Still not finished. We completed our discriminant with respect to this critical point. Now we need to look at it for this critical point. So here we go. So we have, let's write down the notation here. Do 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 do. Oh, bo do do do. Do 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 ba ba. Do do do. Okay, so we have that. Now let's go ahead and figure this out. So this is still going to be 4, all right, just like it was in the previous one. Doesn't matter what this point is because the second partial here is just a constant, so it's 4. This one, though, remember, we got to do something with this because our second partial with respect to y contained a variable. So you replace this 2 into your second partial with respect to y, and you get 12 times 2, which is 24. 24 minus 6 is 18. So we write that down, and then minus, this is going to be 0 squared. And so this is going to generate what? Well, a positive 72. All right, which means it's definitely greater than 0. So we go back to our second partials test, and we know it's either now going to be number 1 or number 2. We need to check our value of our second partial with respect to x because this is greater than 0. So our second partial with respect to x, regardless of the point, is constantly 4, which means it's greater than 0, which means what? Well, which means it's option number 1. So therefore, f has a relative minimum at our critical point 3/2, 2. So let's write that down. We'll just write this down. Relative min, where? At f of 3/2 deuce equaling whatever. Again, you got to be able to plug in this x coordinate into every x, this y coordinate 2 into every y in the given function. If you do that correctly, you'll get a negative 47/2. This is actually your minimum right there. Isn't this fun?